we proved a beautiful theorem, maybe last time or one time before that. We proved that there modular prime number, there always is a primitive group. Let me remind you what the primitive group was. So, theorem is a prime. There exists a residue A of order K-1. Every non-zero residue modulo is the power of this number is a to the power I the sum I. So we prove the following theorem. There is some number modulo p such that first of all its order is exactly p minus 1, the largest possible order. Well, it follows from this set that every number modulo p which is not equal to 0 is some power of this primitive element. So now I want to show kind of funny application of this. Let's compute. So example exercise. So first part. Let's compute the following sum. 1 plus 2 plus and so on plus p minus 1 modulo p. So this particular sum, we can say that it doesn't have much to do with anything about primitive elements. Just what is 0? Okay, so the claim is this sum, 1 plus 2 plus and so on plus p minus 1 is congruent to 0 modulo p. Why is that? Why is it?
First one last one times
Okay, yes. So the reason is, well, one reason. We can actually compute it. This thing, well, here is some well, here is a sum. We can rewrite it in this way. Just take the same sum in the opposite order. Okay, so wait a second. Yeah.
I just want to say that this isn't true for all primes.
For p which is 4, yes, for p equal to 1, the fluid is 1, yes. So, okay, yes. So for now what's written here, okay, yes, you're right, of course. I shouldn't write this. So a for all p, this sum is equal to 0, modulo p. So I can rewrite this thing and we'll compute this sum. If I take twice this sum, I will get what? P plus and so on plus p. So if this sum is s and twice s, this thing which is obviously congruent to 0 modulo p. And now, well, if 2 times s is congruent to 0 modulo p, then s itself is congruent to 0 modulo p. Hence, s is congruent to 0 modulo p. And here I am using the fact that p is actually odd prime. Otherwise, well, it could happen that twice some number is divisible by 2, but the number itself isn't. Okay, so very nice, very simple proof. Maybe if somebody knows the formula right away, you can say that it's p times p minus 1 divided by 2. And since p is odd, it's divisible by p over 12. Yes. So those are ways to solve this exercise. Now what about if I take a similar sum, but now I'm computing 1 to some power I, so I is some integer, plus 2 to the power I, let me go, okay. Plus, so on, plus p minus 1 to the power k. I want to understand precisely what this thing is, modulo p. Here, well, when k is equal to 1, we try to find the answer. If k is 2, if you try to proceed in a similar way, well, what kind of ideas we have? Idea number 1, write down the formula for the sum and try to understand that it is divisible by p. Well, it is a good idea if you can write down the formula. k equal to 2, k equal to 3, maybe some of you know the formulas. Well, I guess at the general k, nobody at least remembers the formula. Maybe you've seen some formulas, what I call binary numbers. That's a complicated formula, it has lots of denominators. It's not going to work. Another idea, well, do something like what we did here. The trick here was like this. Take this sum, and inside of this sum, try to combine different terms. Here we combine the first term and the last one, the sum was divisible by p. Okay, the second one, the second but last, the sum is divisible by p. So maybe something like this is going to work here. Once again, kind of hard to understand what should be combined with what. Yes, difficult to understand. Yes.
Maybe the first one is my last one.
Okay, so if you try 1 to the power k plus p minus 1 to the power k, what is it? Modulo p is the same thing as 1 to the power k plus minus 1 to the power k. When k is odd, this is 0. When k is even, this is 2. So for k equal to 2, this already doesn't work. For k odd, it does work, yes. So this is equal to 0 modulo p if k is odd. In fact, well, if k is odd, we can proceed with this idea and proceed to the end. So a to the power k plus p minus a to the power k, same thing, a to the power k plus minus a to the power k is congruent to 0 modulo p if k is odd. So indeed, for odd k, this shows for odd k and odd p. The sum is 0 modulo p. So I guess the first non-trivial case we encounter is k equal to 2. What about some squares? How can we compute what is sum of squares modulo p? Okay, so indeed, the thing which can be applied for any k is like this. Let me take these numbers from 1 to p minus 1. So numbers, if you write numbers from 1 to p minus 1, you know that they are different powers of the primitive element modulo p. So r permutation of a to the power 0, a to the power 1, up to a to p 2 for the primitive element A modulo P. The reason maybe why we might suspect that such an idea would work is because, well, a primitive element works very nicely when you raise it to different powers. I mean, it's very easy to take a number written in such a form and raise it to any power. You just take this thing and multiply the exponent here by the corresponding power. So what's written here is as follows. Every element from 1 to p minus 1 can be written as some power of A, and this power is from 0 to p minus 2. A to the power 0 is just 1. But other elements, well, they're just some permutation of this number. I mean, I don't know what is A, I don't know what is its square, and so on, but I do know that every number from 1 to p minus 1 is some power of this A. Okay, now what is this sum? 1 to the power k plus and so on plus p minus 1 to the power k. Well, let me write this sum, each element in this form. So I can write this as a to the power 0 times k plus a to the power 1 times k plus and so on plus a to the power p minus 1 times k. Well, here of course it is just the congruence modulo p. Once again, these elements, well, they do not correspond exactly to the same things in the same order, but they do correspond to the same summands in perhaps in different order. Every summand here is one of those, but you don't know which one. P minus 2, yes. Okay, now let me just compute this sum. What is it? It's just different sums, sum of different powers of a to the power k. It's a to the power k to the power 0 plus a to the power k to the power 1 plus a to the power k to the power p minus 1 minus 2. So it's the same number, summation of such things raised to different powers. It's just a geometric series. At each step I'm multiplying by a to the power k. So I have a formula. I can just write inequality. This thing is a to the power k to the power p minus 1 divided by a to the power k minus 1. Here I have an actual equality. Not just congruence, actual equality. It's a formula which is rated just in integers. On the next step, I would want to understand what is this number. And I would want to write something like this. Well, now I have Fermat's little theory. Anything raised to power p minus 1 is equal to 1. So in the numerator I have 1 minus 1 divided by whatever, and this is congruent to 0. So basically I solved the exercise. Actually not quite. I mean, if you just take some particular cases, you'll find out that, well, it's just wrong. Yes. So what happens is the numerator here, denominator here is equal to 0. Well, a is some number, it itself is not equal to 0. It's not even, yes, so a is some positive number, a is not equal to 1, it's a primitive root modulo p, so this number is not equal to 0. But modulo prime, p, it could happen that it is 0. So here I can take this expression related modulo p only if a to the power k is not congruent to 1 modulo p. So now this works. So if the denominator is is not divisible by p, I can complete this computation, and well, here I'm using Fermat's-Newton theorem. A to the power of this thing is congruent to 1 modulo p. Okay. Now let's understand how much we actually missed. So we didn't solve the exercise for every k, only for those for which a to the power k is not equal to 1. What can you say? How can you characterize such case?
K is not equal to P.
Okay, yes. So the order of a is exactly p minus 1. If a to some power is equal to 1 modulo p, it means that this power is divisible by p minus 1. So not quite equal to p minus 1, but rather divisible. So i.e. p minus 1 does not divide k. Yes. So this is because order of a modulo p is exactly p minus 1. It's the smallest power to which you should raise a to get p minus 1, to get 1. Okay, so the conclusion is for every k which is not a multiple of p minus 1, the sum is 0. We can just kind of compute it. Well, not quite on p modulo p, but we can compute it. What if k is divisible by p minus 1? If k is a multiple of p minus 1. Let's go back to the original problem. 1 to the power k plus 2 to the power k plus and so on. Zero. Why is it 0?
It's like 1 to the n and 2 to the n, but it's always P minus 1. So for every number, it's not always 1.
Almost, yes. So you're right, almost. So just the answer is not 0, it's minus 1. P minus 1, yes. So you want to plus something?
But then minus.
Yes, it is minus 1. So k is a multiple of p minus 1. So I can write everything here, every sum is something raised to power p minus 1. Now by Fermat's-Newton theorem, whatever you take and raise it to power p minus 1, you get 1 modulo p. So this thing by Fermat's-Newton theorem is just sum of 1 plus 1 and so on. Exactly p minus 1 times. So it is just p minus 1. Or congruent to minus 1 modulo p. So now we've got a complete answer. This sum 1 to the power k plus 2 to the power k plus so on plus p minus 1 to the power k is congruent, well, either to 0 modulo p, if p minus 1 does not divide k, and if it does, it's just minus 1. So the point of this exercise is, well, not exactly about computing this particular sum. I could have computed, well, lots of different things in similar ways. The point of this exercise is, of course, we used primitive element theory. We used existence of primitive element. We couldn't solve this exercise as easily without this. I mean, there are other ways to solve this exercise, but, well, that's perhaps one of the easiest ones. So we use this fact, we use existence. We didn't know what the primitive element is. And actually it turned out that we actually didn't care. It just didn't matter. At some point, well, we just knew that this formula, the answer doesn't depend on the particular choice of A. Well, it's more or less because the original problem didn't depend on the choice of A. So we should have expected that the answer should not depend on A. Well, but the mere existence allowed you to compute actual numbers in the end. So even though the theorem that we proved existence of primitive element is not really constructed, I didn't tell you a recipe how to take a modulus P and find the primitive element. I didn't tell you that the order of the element 2 is always P minus 1. No, not at all. But sometimes it just doesn't matter. Sometimes all we want is just there is some element of order P minus 1 and it will be sufficient to solve a problem. So maybe any questions about this exercise? Okay. Let me discuss then our favorite equation, x to the power k is equal to b modulo p. Let me start with the following step. So let p be right, a primitive group. Let me try to solve the equation x to the power k is congruent to 1 modulo p. I know it has at least one solution. Does anyone see a solution? One, yes. So 1 to the power k is equal to 1 modulo p. Now I claim that if I know a primitive element, I can write down all possible solutions. Well, indeed, every solution should be some power of the primitive element. So if it has some power of a, sorry, of course, it's not an assumption, it's just, I can write x as a to some power, a to the power I, modulo p. And I know that a to the power I raised to the power k is congruent to 1 modulo p. It's just a translation. I can write a solution as a power of a primitive element because I can write every non-zero number as power of primitive element. And x is of course not zero because its power is 1. Well, but what does it mean? Here it means ID a to the power of I times k is equal to 1 modulo p. The order of a is exactly p minus 1. So it's the same as saying that p minus 1 divides I times k. Let me rewrite this as a condition about I itself. About I itself. If I know that p minus 1 divides the product of I and k, let me try to factor out whatever divides both p minus 1 and k. And then I'm left with, so the rest, whatever I didn't factor out, should divide I. So I can factor out the greatest thing which divides both p minus 1 and k. And this thing should divide I. So in terms of the primitive element, I just find all the solutions. So this equation result, maybe the theorem, it will be definition. I mean, it's really something the theorem is just very simple computation. So x to the power k is congruent to 1 modulo b. Yes. How many distinct solutions do I have? I want all possible multiples of this number. And I want only those which are at most p minus 1. So there are GCD p minus 1 and k, different solutions. And they are a to the power I with I multiple p minus 1 divided by GCD p minus 1 and k. So once again, in this result, part of the result doesn't depend on a particular choice of the primitive root. It just doesn't depend at all. If you want to count how many solutions are there to this equation, here's the complete answer. It's GCD, greatest common divisor of your exponent here, and p minus 1. Example, well, if k is relatively prime to p minus 1, we already considered this case. You know that we can actually solve this thing and say that 1 is the only solution. Another example, if k is equal to p minus 1, Fermat-Little theorem tells you there are p minus 1 distinct solutions. Every non-zero number is a solution. And now we've got a result for everything in between. Whatever k is, this congruence has that many solutions. Second part of the result, well, at least seemingly depends on the choice of the primitive root. I mean, you choose a primitive root, now you raise it to different powers. The powers are multiples of the same number, and this set describes all possible solutions. What happens if you choose a different primitive root? Well, you'll get the same answers. Of course, it should be the same answers with the same equation, but just in different order. So let me write this remark about particular cases. For example, k is relatively prime p minus 1 x equal to 1 is the only solution. Well, in other ways, you can just is equal to p minus 1, then Fermat-Little theorem tells that for instance, Fermat-Little theorem just tells you that all the residues are solutions of this equation. And once again, if k is something in between, not relatively prime, not exactly equal to p minus 1, well, before we prove the existence of primitive element, well, it was hard for us to decide how many solutions are there. Either only one, or either exactly k, or either something. Well, now we have a complete answer. Now something more complicated. So this equation is kind of a very particular form. It's f to the power k is equal to 1. you want to extract kth root out of units, out of the number 1. First of all, you know that there is always at least one solution, and well, if you want to find all possible solutions, you can do it this way.
The first of one there, why one is the only solution?
Okay, so if k is relatively prime to t minus 1,
Yeah.
then you can do the following. So first of all, it's the result of the theorem, of course, that there is only one solution, and here's the solution.
Oh.
But we did know it before this. We knew how to solve a congruence like this. If you take x to the power k is congruent to v modulo p, and GCD of k and p minus 1 is 1. In fact, we have even more general situation. If you want to solve such a congruence and the GCD of k and 5n is equal to 1, then you know that x can be just written as b to some power s modulo n, where s is just 1 over k considered modulo 5n. So we get s times k is congruent to 1 modulo 5n. So you get a very general result. If you want to solve such a congruence modulo in fact any number without existence of whatever, primitive roots, without any hard results, we can just show that there is only one solution. There always is a solution. It is unique and it is given by a very simple formula. So much more complete result than that. Here we don't have a result which is as good. We don't really have a formula for the solutions of this equation. And in our formula, that one depends on the choice of primitive element. And you know a primitive element is actually hard to find. If you take a large number p, you might have to work quite a bit to actually find a primitive element. But the number of solutions is very easy to find. So maybe let me compare this to the real case. So here we could have quite a lot of options for how many solutions are there. What about the number of solutions of this equation x to the power k equal to 1 in real numbers? If you want how many different roots of number 1 are there in real numbers? Maybe if k is, let's think, if k is 2. X squared is equal to 1 in real numbers. What are the solutions? Plus minus 1, right. What about, say, 4? X to the power 4 is equal to 1. Same, still plus or minus 1. X to any even number is equal to 1. There's only two solutions in real numbers. It's either 1 or minus 1. If you take a number whose absolute value is not equal to 1, raised to any power, it's still not going to be 1. So there are only two options to check, 1 and minus 1. If k is even, both work. If k is odd, only one works. So in real numbers, this equation has always either one solution or two solutions. That's it. If you know complex numbers, you know that, well, I'm not going to use this later, but if you know complex numbers, you know that this equation has always k distinct solutions, and there is nice geometric descriptions of those. They lie at vertices of regular k-gon on the unit circle. So in complex numbers, the number of solutions is always k. Once again, it depends only slightly on the particular shape of k. But in these kind of numbers, if you consider the numbers only up to adding the multiple of prime number p, well, you have a complicated answer. We fix the prime p, we fix k, well, the number of solutions could be basically any divisor of p minus 1. So, quite a lot of different options. Okay, so now I want to consider a slightly more general equation. X to the power k is congruent to some number b. So more generally, let's try to understand what happens if we try to solve such a complex. Unfortunately, the question of whether this congruence has at least one solution is not obvious. In that case, we did see just solid solution. One x equal to 1 is a solution. Here it's not obvious. This congruence might have no solutions. It might have lots of solutions. So an example with no solutions maybe x squared is congruent to
2 now.
okay, yes, 2, 1, 3. Yes, no solutions. Example. But of course it could have solutions. X squared is equal to 1, modulo 3 does have solutions. And we know that when b is equal to 1, we can count the number of solutions. So what happens for other values of b? Well, let me suppose that there is at least one solution. Can we describe all others? So suppose x to the power of k is congruent to b modulo b has at least one solution. And I can give it a name, it's not. Well, one of the options is that this number is 0, and then b is equal to 0, and then the equation is not interesting. So we get rid of this option in the very beginning, because, well, it's kind of different from that other part of the story. So if b is congruent to 0, then x to the power k is congruent to b modulo p has one solution. And it is 0. Indeed, if x to some power is divisible by p, then x itself is divisible by this prime number p. If b is not equal to 0, then, well, first of all, my solution is not congruent to 0. So let me take any solution of this equation and divide it by this particular solution. So consider y, which is x times the inverse of x naught. So let me divide a solution of my equation by some particular chosen solution, x naught. This number y raised to the power k. What is it? It's x times inverse of x naught raised to the power k. In other words, it's x to the power k times x naught to the power minus k. But I know that both of them are solutions of this equation. So it is b times inverse of b. So it is 1. What we just, well, i.e. y to the power k is a solution, sorry, i.e. y is a solution of y to the power k is equal to 1 modulo p. But we already know what to do with this equation. 16 solutions. You know how to describe them, have a primitive element. So we are quite comfortable with this equation. So what is just said here is, if you have two different solutions of this equation, then their quotient is a solution of this equation. Oh, vice versa, it works just as well. If I have a solution of this equation, and I take any solution of that equation, the product will be another solution of that equation. Let me explain it when k is equal to 2. It's really, really simple. If I have one square root of some number b, then any square root is either the one that I already have, or just minus whatever I found. If I want to solve the equation x squared is equal to b, well, one option is there are just no solutions. Another option, I do find the square root, but then I have plus or minus the square root. And this plus or minus, why do they appear? Because plus 1 and minus 1 are exactly the solutions of the congruence x squared is congruent to 1. There's the square roots of 1. The same happens for any k, just any. This congruence could have 0 solutions. Yes, it could. It happens. If it has at least one solution, then every other solution is a product of this particular one and some root of 1. So let me write this opposite direction as well, vice versa. If y to the power k is congruent to 1 modulo p, then x, which is x naught times y, so x to the power p is congruent to b. Well, the result is scopes. How many solutions does it? So maybe that's already a theorem. Number of solutions of x to the power k is congruent to b modulo p is, well, 1 if b is equal to 0 modulo p, just could happen that it's 0. If you're unfortunate enough to choose a b which is, well, just not any case power of some element, well, would have 0 solutions. But if it is not equal to 0, if you have at least one solution, you can multiply the solution by any solution of this equation y to the power k is equal to 1, by any k's root of unity, and get another solution. And then you get, well, as many solutions as there are roots of unity of order k. How many are there? Well, we just computed this number. It is GCD k and p minus 1. Solutions. The quotient of any two of them and the quotient consider already first any questions about this. Let's consider some very simple numerical example and have a short break. So, example, let me take a equal to 3, b equal to 7. So, if I want to solve x cubed is congruent to 0, modulo to 7, well, I have one solution. This system is very simple to analyze always. I mean, if this number is prime, then this is just the same thing. Another thing, what are the roots of, well, if you want to solve this equation, no, you know that it has 3 solutions. That's part of the general theory. This 3 is a divisor of 7 minus 1, so GCD of 7 minus 1 and 3 is exactly 3. This equation has 3 solutions. One of them is 1. The other solutions, well, now we have several options. One of them is, I mean, if you are really serious about doing arithmetics, modulo 7, modulo this prime number, and we have lots of problems to solve, then probably you should just find the primitive root and work with it later. But if you have no way of reusing this primitive root, then maybe it's faster indeed just to guess. So yes, 2 is a solution. And by the way, if you know one solution to this equation, any power of it is also a solution. So 2 and then 4. So let's just consider a third equation. X cubed is equal to minus 1 modulo 7. Well, one solution is obvious. What is? Oh yes, negative 1 cubed is always negative 1, not only modulo 7. So x is congruent to negative 1 is a solution. And now we can use the following method. If we have any solution, if we found just one, we can multiply it by any root of unity of order 3, by any cubic root of unity, and get another solution. In this way, we are going to get all solutions. So x equal to negative 2, x equal to negative 4. Are all solutions. So cubic roots of 1 are right here. It's 1, 2, and 4. It is modulo 7. And here are all the solutions. You find one of them, you found all of them. Well, and finally, x cubed is congruent to 2 modulo 7 has no solutions. Does anyone see why? Well, we are going to see a better reason later today, but for now, because we just know, we just exhausted all possibilities. These residues, when you cube them, you get 1. For those residues, you get minus 1. For 0, you get 0. And that's it. We covered 7 different possibilities. So, we just computed everything. So in a sense, we analyze this equation, well, this equation we analyze completely. But in general, the equation x to the power k is congruent to v modulo prime number, well, we almost analyze it completely. We still have no way to understand whether it has 0 solutions or it has, well, GCD of k and p minus 1 solutions. So we'll talk about this of the debris.